Welcome to the Explainer. You know, we're always looking at how things change, but today we're talking about something special. We're going to uncover the hidden rules, the secret math behind those huge, dramatic, out-of-nowhere shifts you see all around you.
So what do these things have in common? It sounds like the start of a bad joke, right? But the answer is actually incredible. It points to a deep, fundamental pattern in how pretty much everything works. It's like a secret language of change.
Yep, you guessed it. They're all governed by the mathematics of sudden change. Think about that for a second. All of these systems, which seem totally different, can hit a point where one tiny little nudge, a smooth, continuous change, suddenly triggers a massive, system-wide transformation. Like a faucet going from a steady drip, drip, drip to just a chaotic mess of water. The whole character of the system changes in an instant.
All right, so here's how we're going to break this down. First, we'll talk about something we all kind of get. Tipping points. Then we'll put a real name on it. What exactly is a bifurcation? We'll look at its two main flavors, local versus global, and check out some cool examples. And finally, we'll get to the big question. Why does any of this matter? Let's dive in.
Okay, first up, the world's tipping points. Before we even touch the heavy-duty math, let's just build up our intuition. We're going to start with an idea that I think everybody understands, at least on a gut level.
You know how it is. So many things in the world, they just bend. They stretch, they change slowly and predictably, and then boom, all at once, they just snap into a completely new state. It's like bending a plastic ruler, right? It flexes, it flexes, it flexes, and then crack, it's broken. Or a low murmur in a crowd that just builds and builds until suddenly it becomes a deafening roar. That snap, that sudden shift, is exactly what we're talking about today.
All right. So this snap isn't just a vague idea. It actually has a proper mathematical name. So let's get to it. What is a bifurcation? And who is the genius who first put a name to this whole phenomenon?
Okay, here's the official definition. Bifurcation theory is the mathematical study of changes in the qualitative structure of a system. And that word qualitative is absolutely key. We're not just talking about numbers going up or down. We're talking about the whole behavior, the entire nature of the system, fundamentally transforming. The faucet doesn't just drip faster, it stops being a dripper and becomes a streamer. The rules of the game have changed, all because you nudged one little parameter past a critical point.
And to find the origin of this idea, we have to go back in time, way back to 1885. This is where a true legend of math and physics enters the picture.
That's right. The name bifurcation was first introduced by the one and only Henri Poincaré. He was working on this incredibly complex problem about the stability of rotating fluids, and in his paper, he became the first person to ever mathematically describe one of these tipping points. He literally gave us the language to talk about this, and in doing so, he laid the foundation for huge fields like chaos theory.
Okay, so here's where it gets even more interesting. It turns out not all of these sudden shifts are the same. They really come in two main flavors, local and global. And it's all about the scale of the change.
And this comparison just nails the difference. A local bifurcation, think of it like flipping a light switch. The change is, it's local. It happens right around a specific point, and it's pretty predictable. It goes from off to on. But a global bifurcation, whoa, that's like a dam breaking. We're not talking about a small, contained change. We're talking about a massive, system-wide event where huge parts of the system's possible behaviors collide and just completely rewrite the rules. All right, let's make this real. Enough with the abstract ideas. We're going to look at a classic example from each category to see these bifurcations in action. Let's kick things off with a super famous local one that takes us on a pretty wild ride.
So, a really common local bifurcation is something called the period doubling cascade. And get this, it's a famous route to chaos. Imagine a system that's just ticking along with a simple, stable rhythm. A nice, predictable cycle. Now you start to tweak a parameter, just turning a knob a little bit. All of a sudden, that simple cycle becomes unstable, and it splits into a new cycle that takes twice as long to repeat. Turn the knob a bit more, it splits again. Now it's 4 times as long. Then 8, then 16, and it happens faster and faster until, boom, the behavior isn't periodic at all anymore. It's just pure chaos.
Okay, now for the global side of things. A classic example here is the homoclinic bifurcation. And if period doubling was a route to chaos, this one is just, it's catastrophic. We're not talking about a cycle splitting and getting more complicated. We're talking about a stable, predictable pattern getting completely wiped out. Just gone.
So how does this happen?
Well, let's walk through it. First, you've got a system with a nice, stable orbit. Everything is chugging along predictably. Then, as you change that parameter, the orbit starts to expand. It gets bigger and bigger until it collides with a critical point in the system called a saddle point. And the moment they touch, poof, the entire stable orbit is just destroyed. It completely vanishes from existence in an instant.
Okay, so this is all really cool, right? But I know what you might be thinking. This is some pretty abstract math. Does it actually matter in the real world? And the answer is a huge, emphatic yes. The applications are absolutely incredible.
I mean, look at this list. Laser dynamics, quantum systems, the behavior of atoms and molecules. This isn't just a mathematical curiosity. Bifurcation theory is an essential tool for understanding, predicting, and even controlling some of the most complex systems in modern physics and engineering. These tipping points are literally everywhere.
And this is maybe the most profound part of all. Bifurcations provide this incredible, powerful link between the world we're used to, the predictable, classical physics of everyday objects, and the truly bizarre world of quantum mechanics. What happens is, at these bifurcation points, the behavior of classical orbits gets so amplified, so pronounced, that you can actually see their signatures pop up clearly in quantum systems. It's like a bridge between two different realities.
All right, let's bring it all home. As we wrap this up, I want to focus on the single biggest takeaway, the secret pattern of change that this whole theory reveals.
See, bifurcation theory isn't just a bunch of equations. It's more like a language. It's a language that describes a fundamental pattern of the universe, how stability suddenly gives way to change. It teaches us that these big, dramatic shifts, they're not always random. They're not just bolts from the blue. Very often, they follow predictable mathematical rules. It's the science of the breaking point.
And that leaves us with a pretty provocative question, doesn't it? If these tiny, smooth changes can really trigger huge, sudden shifts, what bifurcation might we be approaching right now? Because this framework, this way of thinking, it doesn't just stop with physics. It gives us a whole new lens to look at change in technology, in our climate, even in our own societies. It makes you wonder, what are the hidden knobs being turned, and how close are we to the next big snap?